For this example, we're going to compute probabilities with the general multiplication rule. So we're told that we just received a shipment of 11 televisions. 3 of them are defective, 2 are randomly selected, and then we're asked to compute the probability that both televisions work. That's the first part of this problem. Now, we're using the general rule here because these events are not independent. In other words, it will depend on what we select with our first random selection as to what we get when we randomly select that second television. The probabilities may be or will be different because we have changed what is in our sample space. Remember, some of these are defective and some are not, and we're not replacing what we select. So we could write this in a couple of ways. We could use the more mathematical notation. We could say, okay, I'm going to find the probability that the first television works, and that general multiplication rule says then I'm going to multiply this by the probability the second television works, given that the first one works. So here's where that dependence piece plays in. And so I could just go ahead and find those values. So the probability that the first TV works would be, let's see, we have 11 TVs, 3 are defective, so there's 8 out of 11 for the first one. But remember that you just selected one that works for that first selection, so now you're down to a total sample space of 10, and you're down one working TV as well to select for the second TV. So in other words, this is what we end up with as our probabilities individually for each selection, and then we multiply that through to get the probability that both televisions work. And that must be approximately 0.509. Another way to do this, though, is to visualize it in a tree diagram. And this is one method that I prefer, personally. So I make a selection. Think of these 2 branches as the first selection. There's one of 2 things could happen here. It could work, or it could not work. Now, the probability that that first television works is the total number of correctly working televisions over the total number of TVs in the shipment. The probability that it doesn't work is the total number of defective over the total number of TVs in the shipment. Okay, so that's the first selection. I'm going to go with a different color here because from here we make a second selection. And again, one of 2 things could happen. It could work or not work. And I'm just going to go from this first branch to begin with. So remember now, we've already selected one TV. So we're now down to a sample space of 10, of which if I select one that works, now there's only 7 TVs that remain that work out of 10 TVs that remain. But there's still 3 defective TVs, but again, out of 10 that will not work. So that's one way to kind of visualize what could happen, all the different possibilities. I could even complete this tree diagram and write out what happens if my first selection did not work. And I'm going to pause the video and fill those in, but just go back and verify that you get the same value. So if you check, make sure that you have these same values along these branches. The difference here is that your first selection did not work. So now you don't have 3 defective TVs, you only have 2. Okay, so to use the tree diagram to then find a probability, we'll multiply through the branches. So you're using still the general multiplication rule. You're still multiplying, but it kind of does this piece for you, the given piece. So we want to pick a TV that works for the first selection and the second selection. So these are the two values that we multiply. Notice that's the same thing as if we had used the formula. So just a different option there. For the next part, we're asked to find the probability that at least one of the two televisions does not work. So this would be a good place to use that at least formula. So to find the probability that at least one does not work, we would do 1 minus the probability that they both work. Luckily, that's what we just found above. So that is 1 minus 0.509, which is 0.491.